The next two equations on your datasheet for Unit 1 kind of go together because they're both efficiency. One of them is your useful energy and one of them is your useful power. Both times though, you've got to decide what is it in the process that is the useful energy or the useful power. So think about the purpose of the electrical appliance perhaps that you're looking at. If it was a light bulb, then the useful energy would be the light energy, not the heat that is generated. The heat is wasted energy. You might be given a Sankey diagram to go with this. A Sankey diagram is a way of representing the different proportions of energy. So you'll have the energy input, and because energy can't be created or destroyed, your energy output here and here will be equal to the total input. So if you added together all the little squares for your useful and wasted energy, it would be equal to your energy input. If we want to calculate the efficiency, again we're looking at the useful output. So if our useful output was 6 little squares and the wasted energy was 14 little squares, 6 and 14 gives us the energy input of 20. So the useful is 6 out of the 20 that were inputted, so it gives us an efficiency of 0.3. I would actually times this by 100 to give you an efficiency as a percentage, because that's what the equation on the datasheet suggests. So it'd be 0.3 times by 100 would give us 30% efficiency here. In this past paper example, it says burning 1 kilogram of wood transfers 15 megajoules of energy to the stove. The stove then transfers 13.5 megajoules of energy to the room. Calculate the efficiency. So if we have 15 megajoules transferred to the stove and 13.5 of that is useful, the efficiency equation, which I would copy out from the physics equation sheet, is our useful divided by our total times by 100. So here we would have our useful, which is 13.5, divided by our total, which is 15, and then times by 100 to give us an efficiency percentage. So you should find that this is 90% efficient. Notice that I wasn't really that bothered about what the megajoules here stands for. Both things have the same units, so when you divide it'll cancel it out. A megajoule is actually 1 million joules, but it doesn't matter because if I do 15 million and 13.5 million, the two things will cancel each other out. So don't panic if you see an unfamiliar unit in efficiency calculations. They will just cancel out provided both things have the same units.